Hey guys, this is Professor Janacek, and I want to talk about improper integrals. We say that integrals with one or more infinite limits and or discontinuous integrands are called improper integrals. We can talk about these being either convergent or divergent. Convergent is if the limit exists and has a finite value, whereas divergent is if the limit does not exist or it has an infinite value. Now to begin with, if we have an integral that goes from a to infinity, where the upper limit of integration is infinity, the way we'll work this is we'll take the limit as some value t goes to positive infinity of the integral from a to t of f of x dx. Now if our integral goes from negative infinity to b, where the lower limit of integration now is negative infinity, we'll treat that in a similar manner. We'll take the limit as t approaches negative infinity of the integral from t to b of f of x dx. Now, if we have both limits of integration are going to infinity, one in the negative and one in the positive direction, so we're going to take the integral from negative infinity to positive infinity of f of x dx, we'll actually split this up and go from negative infinity to some value, I'll call it c of f of x dx, plus the integral from c to infinity of f of x dx. So we actually split this up into the two previous cases. So the first integral looks like our second case, and our second integral looks like our first case. And so each of these, of course, we would have to rewrite as limits. So this is just the first step. The next step would be to write those as limits. Now, in order for this to be convergent, both integrals independently must also be convergent. Now, what if there is a discontinuity at a, at one of those limits of integration? Notice I'm integrating from a to b. Well, we'll deal with this in a somewhat similar manner. We'll take the limit as t approaches a, but only from the right-hand side. And then we'll integrate from t to b. If we have a discontinuity at b, and notice we're going to integrate again from a to b, again, in a similar technique, we'll take the limit as t approaches b, where our discontinuity is, from the left-hand side. And then we'll integrate from a to t. So notice, if the discontinuity is at the lower limit of integration, we can only integrate from within that interval of integration, so only from the right-hand side. Whereas if the upper limit of integration is where the discontinuity occurs, again, we can only integrate from with that interval, so we'd have to integrate from the left-hand side as we approach that limit of integration. Now, if there is a discontinuity at c, where c is somewhere within our interval of integration, as we integrate from a to b, we'll again have to split it up, and we'll integrate from a to c, oops, yeah, that's right, okay, plus, make that look more like an A, and then from C to B. And so notice in this situation, this first integral has a discontinuity in the upper spot, as we see here. So we would have to set up that limit, set up a limit for that first one. For the second one, it's sort of like the other case where the discontinuity is at the A position, right, at the lower end. So we would have to set up a limit. So again, what we see is this is just our initial step. Then from here, we would have to write each integral as a limit of a new integral. Let's try some examples. Let's take a look at the integral from 0 to infinity of e to the negative 3x dx. So the first thing we're going to do is we're going to set this up as a limit. We're going to take the limit, I'll say as b goes to infinity, of the integral from 0 to b of e to the negative 3x dx. Well, in order to integrate this, it might be useful to remember that we'll need that negative 3 as that different and that part of our differential. So when we take that limit, we end up with negative 1/3 e to the negative 3x, and we'll evaluate that from 0 to b. Notice I still have that limit on there. Don't forget, once you write that down, make sure you always include that limit there in the front until you evaluate the limit. I'm not going to evaluate that limit just yet. I still want to go ahead and evaluate it from 0 to b. So that's what we'll do next. So we still have the limit as b goes to infinity of negative 1/3 e to the negative 3 times b minus a negative 1/3 e to the negative 3 times 0. So let me simplify this before I evaluate the limit. So I still have this limit notation. So let's start with this one. This is going to be the easy one, a little easier at least. So first off, I have minus a negative, so that makes that whole thing a positive. 0 in the exponent means that e to the negative 3 times 0 is all that's going to be 1. So that whole thing ends up being just 1/3. Then this other one, the only thing I'm going to do here, of course, it is negative in front, so it's going to be subtraction. But then this negative in the exponent really means that that whole e is in the denominator. So we end up with minus 1/3 e to the 3b. Let me write that a little clearer. Oops, that's now positive. All right, so again, make sure you understand where everything went. The 0 in this exponent makes this e 1. Of course, we've got a positive there in front of it now. And then the negative in this exponent brings that whole e down to the denominator. Now, I'm taking the limit as b goes to infinity. In other words, b is getting really large. My exponent here is getting really large. Anything, including e, raised to a really large number is a really large number. So this whole denominator is getting very, very big, which means this whole fraction is getting very, very small. So now when I take the limit, notice there are no b's in this part, so that stays as is. However, this part goes to 0. So we end up getting 1/3 minus 0, which is, of course, 1/3. And there you go. So we do have to remember not only how to take limits here, but also how to integrate. So kind of a combination of two different things. All right, let's take a look here at example 2. We're going to integrate from negative infinity to positive infinity of dx over 1 plus x squared. All right, first thing I want to do, I already have this integral written. First thing I want to do is to write this as two separate integrals, one going from negative infinity up to some number. I'll go ahead and pick a number, pick something between negative infinity. I'll pick 0. And I also want to go ahead and write that dx off to the side. It's not required, but I know a lot of people prefer that. And then I'm going to add to that the integral going from 0 to positive infinity. So just split it up into two separate integrals. Now, each of these integrals need to be written as limits. So the first one, I'm going to take the limit as a goes to negative infinity of the integral from a to 0. The second one, I'll write as the limit as b goes to positive infinity of the integral from 0 to b. And now we simply have to integrate. Now, if you don't recognize this, hopefully here in a second you will, if we integrate 1 over 1 plus x squared, we end up with the inverse tangent of x. So the first one, of course, is being evaluated from a to 0. And the second one, is being evaluated from 0 to b. Of course, we're taking the limit of each of those. Be careful with that. All right, so let's see if we can evaluate. Again, I'm going to go ahead and evaluate the first one from a to 0, the second one from 0 to b. So we get the limit. Still keep that limit notation on each of those. Second one, again, keep that limit notation on there. Oh, and I think I left off, there's a negative infinity. Hard to see there. All right. The second one is going to positive infinity. Right, now we do have to remember the inverse tangent. Oh, goodness. I think it's going to be useful if we graph this. So if we graph y equals to the inverse tangent of x, what does that look like? Just as a reference, I'll put it over here. Well, we have an asymptote at negative pi over 2 and an asymptote up at positive pi over 2. And it ends up looking something like that. So, using that graph, the inverse tangent of 0, I've got in both spots, that's just 0. Right? So again, evaluating that limit, this first piece becomes 0. And this last piece becomes 0. Now, how about as a goes to negative infinity? So a is getting really, really small in the negative direction, going further and further to negative infinity. What do we get for the inverse tangent of a? Well, looking at our graph, negative infinity is going this way, and it looks like our graph is getting close to negative pi over 2. Oops. Now, as b goes to positive infinity, the inverse tangent of b, again looking at our graph, as we get larger and larger and larger on that graph, it looks like that graph is going up to positive pi over 2. So, doing this simple arithmetic, watch those positives and negatives. This is minus a negative here. So we end up with pi over 2 plus pi over 2, which is simply pi. So there we go. Enjoy!